become useful. All right, so let's start. I have torque, net, K rot, and L, and if you know what those stand for. So we know that torque, I'm really getting bad at drawing that, is force times radius times the sine of the angle between the force and the radial arm. So if I have just a lever arm, so I'm going to attach to this, and this is my pivot point. If I apply a force here, I'm talking about this angle. I only want the perpendicular component of that. And so when I'm dealing with multiple forces, torque net, more correctly written as the sum of all torques, is just really going to be the mathematical sum of these. So I would have taken, if it's on a bar like this, we take each force times its radius away and calculate it. And if it's not, if it's at 90 degrees, the sine of 90 is 1, so that's easy. But where that applies to objects that are rotating, we did that in fixed objects. But what if it's going to be rotating? Well, if I have a set of wheels that are different radii, and I'll put a force on each of them, and put a black pen up little right. If I apply a force here, and a force there, and a force there, I have 3 forces acting. We have to establish a direction of rotation, and by standard, our direction of rotation would be counterclockwise to be positive. And we'll call this force 1, force 2, force 3. And they're at, we'll call this small diameter little r and the large diameter big R. Then the sum of the torques in this statement would be equal to, or torque net, positive forces. First, I've got F2 at R, and I've got F3 at R, and then I'm going to take away F1 at R. So that's how we, just to make sure we remember how to get to that.
Why did you put them in that order?
I just chose to. Order is irrelevant because, so if I've chosen this direction to be positive, force 3 and force 2 are trying to rotate the system in a counterclockwise direction, which is positive. So I made them first, which are positive. And then I chose this one to be negative because it's trying to spin in the other direction. Right. Okay. And so we're able to just kind of choose those constraints. If I want to make clockwise positive because it's going to be convenient for me, then I can do that as well. But the traditional standard is to have counterclockwise to be positive. Okay. And then from that, we come to the statement, the torque net equals I of the system times alpha. All right. And so that would be, we would have to take this statement to find the torque net value and set that equal to the I of the system. I'd say of the system because I could have multiple components tied together. It's the I of whatever it is we're looking at rotating. Okay. So a typical process here, remember the Atwood's machine lab, we had the disk that had mass, and I'm going to start with just one simple mass, little m. G, we'll say the disk has mass m and has a radius r. Given that, the sum of the torques, so when you think about the force, we have mg down, and it has force tension up. And that means the force tension is pulling on the pulley. So when I do the statement for torque net equals I alpha, well, the only torque is the force tension. It's acting at the radius, right? And so we have a theoretical value for the acceleration. The angular acceleration would be that force tension times radius divided by the moment And so I would replace that up here. So the theoretical acceleration, angular acceleration, would be the mg minus ma times the radius of the big wheel divided by the moment of inertia. And if it's a disk, then it's going to be 1/2 m r squared. And so we can actually reduce this down just a little bit. And so one of the r's divides out. Take the half, invert it, and put it up top. And so alpha would be equal to 2 mg minus ma divided by big M r. And so that would be our theoretical angular acceleration that we come up with. So again, we're taking the idea the torque net is simply the only forces acting at radii trying to cause rotation. And then we're able to solve down for what A should be. Well, alpha is A over R. And so I can actually get the R out of the way. And so the theoretical linear acceleration of this mass that falls would be 2 mg minus ma simply divided by the mass of the disk. Went off screen there. And so these two are the same statement. They're just solved for different perspectives. So
wouldn't it be mr squared on the?
I had r on top and r squared on the bottom, so the r divided.
I didn't see it.
It's okay. And so that's a straightforward. Now, what if I had two masses like we did in the lab where we had the Atwood's machine? Well, the process is very similar, except now I have two torques acting. So let's kind of draw that in here. I have, we'll call it M1 on this side. And we had M2 on this side. And so I would have, we have M1G, which causes force tension 1. And we have M2G, which causes force tension 2. Well, force tension 2 is going to try to rotate it counterclockwise, right? And force tension 1 will try to rotate it clockwise. This would be the case where I would say, because I'm assuming this one is heavier, I would choose that to be my positive direction, just because it's going to make my algebra make more sense. And so I then would write the statement that torque net equals I alpha, and that'll be equal to force tension 1 radius minus force tension 2 radius. I would be half mr squared, so half mr squared. Alpha is A over R, so A over R equals, and if I look at this, I have force tension 1 minus force tension 2 times R. And so then the R can divide out of both sides. This becomes, if I multiply through, it becomes R squared. So all the R's go away. And we end up with A equals the difference in tensions divided by, well, twice the difference in tension. So I do the inverse there, divided by the mass of this. So it's very much the same. And how do I get the tension values? Well, I have to come back and look at this. They're both going to have the same linear acceleration. And so I'd write an F net statement for particle 1. F net 1 equals M1A, M1G minus force tension 1. So force tension 1 would be equal to M1G minus M1A. And then force tension 2, or so F net 2, M2A. Well, if that's positive, that means force tension 2 is positive. And so force tension 2 will be equal to M2A plus M2G. And so I can actually plug these numbers in here. And I would have to recombine it because I have A in multiple terms, but then I could still solve for what A should be given that system, right? And what I have here, I'm going to have M1G, and I'm going to be subtracting M2G from it. So once I factor that out, it's going to come out times G. And so what it works out to be it's going to be equal to the difference over the sum. When I reduce it down, it's 2 m1 minus m2 divided by m times g. That would be the theoretical acceleration when I get down to it. So that would be what we find in the Atwood's machine. What's the A we should get. Now we actually took the stopwatch and timed it following to figure out what we did get. Okay, so anytime you have a torque net, you may need to go through this process. So let me give you another little problem to think about. I'm not very good at drawing, so you're just going to work with me. Let's take a wheel whose radius, let's make it 0.2 meters to make the math simple to work with. We'll make the mass of that wheel 1.2 kilograms, kind of off the screen there. And attached to that, we're going to put another wheel, and its mass is going to be 0.4 kilograms. And its radius, we'll make it 0.1 meters just to keep it consistently and easy to do. And to that, let's attach on the here, we'll just put I'm going to hang a weight, force tension. We're going to pull on a rope of, let's say, at 10 newtons. And then on the other one, we're going to take also and pull a rope. We'll make it 5 newtons. And then ask the question, what will be the angular acceleration of the disk? Do you see a path to solving that? Of the system? Anybody? I hear silence. Start with the statement. Torque net equals I alpha. What forces are causing torques? We'll label these 1 and 2. Hello, is this mic on? Anybody there?
Yeah.
So what forces are going to try to cause acceleration or torque?
The tension forces.
The two tensions, right. So my torque net will be equal to force tension 1, and it's acting at radius 1, right? And is it in the same direction or opposite direction of force tension 2?
Same.
The same.
So then they're positive together, right? And what's I?
1/2. Wait.
I have
1/2 mr squared.
that's I1, and I2 is 1/2 m2 r2 squared. Well, I'll call this one 1 and this one 2. So I've got a total I that'll be equal to 1/2 m1 r1 squared plus 1/2 m2 r2 squared. That's my total I. So that's what I'm going to put in place of I there. So when I have multiple pieces, then I have to take into account their effect on the system. And so it actually would just, I could come out and solve a number here. So alpha, let's just narrow this down. Alpha will be equal to force tension 1, radius 1, plus force tension 2, radius 2, divided by I, where I is 1/2 m1 r1 squared plus 1/2 m2 r2 squared. And so we plug in the numbers and go with it, right? So I don't know if this is a big acceleration or not, small radii, but the mass of the pulley makes a difference, right? the mass of this disc, whatever it is. I mean, and 1.8 kilograms, that's only about 4 pounds, but still it's going to be hard to get up. You know, it takes effort to overcome that. And so then you plug it in. So yeah, when you have a problem you don't know, you start with this statement, identify any torques that are acting to cause torque net, make sure that they're signed positive or negative or correct. I didn't draw here, but we should have identified a direction as positive on the system to separate that out. Okay. So whenever you're doing a torque problem, if it's going to rotate, you have to start with this idea. Now, if it doesn't accelerate, it equals 0, which is convenient. Makes, you know, solving the problem much better. But yes, if you have multiple shapes, you have to add the moment of inertia of each shape to get the overall moment of inertia for this statement. Any questions? No. Not standing up. Well, if one comes up, you know how to get a hold of me. So another idea, rotational kinetic energy. Now, we've talked about this briefly. It's written as K ROT, and it is 1/2 of the moment of inertia times the angular speed squared. So the most common method of this, I have a ball rolling that way at a velocity v. If I want to know the total energy, total kinetic energy will be equal to the K translational plus the K rot. So it's 1/2 mv squared plus 1/2 I omega squared. Okay. If it's just spinning in place, if it's just something sitting in like a sphere sitting there spinning, then it has no translational. And translational means in a straight line. So it doesn't have that. So if it's moving at this, then the total kinetic energy would be this. Well, a ball. Yeah, I have a ball. We'll say a solid sphere is 2/5 mr squared, right? Where it has a value, and omega is equal to v over r by definition. And so our K rot, we'll just look at this, 1/2 mv squared plus 1/2 of I, which is 2/5 mr squared, times omega squared, which is v over r squared. And so if I play this little math game, 2/5 times 1/2 is 1/5. And I have r squared here. When I square this, I have r squared there. Those will divide out, and I'm just left with v squared. And so that the total kinetic energy of the ball that is rolling is 1/2 plus 1/5. That's 7/10 mv squared. Okay. So if it is just sitting and spinning, it has rotational kinetic energy. If it's also rolling down a surface, it has linear energy as well as rotational energy. So to add those together. If you try to come up with a for example that makes sense, I don't know, a baseball is coming to mind, but I can't do any math with it because I don't know the mass of anything. If you throw a baseball that doesn't spin, it does have translational kinetic energy. But if you throw it with rotation, some of the force, and if anybody's a pitcher, you can correct me, when you let go of the ball, you cause the ball to have a spin. And so as it's moving toward you, it has both a translational kinetic energy and a rotational kinetic energy. And when you hit the ball, that spin actually interacts and it twists the bat. So a lot of times, and so if the bat is the side view of the bat, if the ball is coming in up here, and let's say it has a rotation in this direction, when it interacts with the bat, that rotation stops and reverses and spins the other direction. This is actually probably the most common direction the ball's rotating when it comes into the bat. It's got a velocity this way, but what will happen is that this will cause a pop fly because the rotational direction of the ball is going to reverse when it interacts with the bat, because your grip on the bat is usually pretty strong, and so it's not going to cause the bat to rotate, and so the ball's rotation stops and begins in the other direction, and so it's actually going to create a pop-up. what you're objective to do is to actually hit that ball straight on. You want to come in at the center of mass of the bat. And so this rotation that it has, when it rotates the other way, is actually going to cause it, it's going to be at this axis point, is actually going to cause it to hit the ground. It's going to have a rotation that would drive it into the downward position. That's just some weird stuff. There's actually a book called The Physics of Baseball. If you're into baseball, it's a very good read once you understand a little more content here. Okay, so let's take a problem that is a lab. You've done this in a sense. I have a table. All right. We'll say that the height of the table is 0.7 meters, just for fun. And we've got a ball. Let's say the mass of the ball is 50 grams. And the radius of the ball is 3 centimeters. Okay. If we drop it from a height of 0.5 meters, and it rolls down this ramp, where will the ball land? As a question. Now, before we knew anything about rotation, you would just take, you know, the old school, I'll do it in green. You do U gravitational at the top equals kinetic energy at the bottom. We find the kinetic energy of the ball right there. And then we would pretend that it left the, we use that to find the velocity. So velocity would be the root of 2gh, right? And it would leave with a tangential velocity, and we would do the time of flight. It's a horizontal, so a projectile here coming off horizontally. We'd see the time of flight is 2y over g square root. That's the time. And then we do v is delta x over t, and so delta x would be root of 2gh times root of, where h is this height, 2y over g, right? That's how we find x, but it's rotating. So how do we deal with it since it's rotating? Well, at the top, it definitely has U gravitational, has UG. At the bottom, it definitely has K, but it's also got K rot. So we need to find the velocity at which it leaves the surface. So we do the same math I just did a minute ago. MGH equals half mv squared plus half I omega squared. So what I'm saying is some of the kinetic energy actually goes into causing the ball to rotate. And so the mgh plus half mv squared plus half of 2/5 mr squared, omega squared is v squared over r squared. And so all of a sudden the mass of the ball doesn't matter, it's in every term. And the 2's will go away, we end up with 1/5, and the r's will go away. And so we end up with GH equals 7/10 v squared. And so v will be the root of 10/7 GH. All right, that would be my velocity. Well, once it leaves, the time is still the same. So then my delta x will be actually the root of 10/7 GH times the root of 2y over g. And I could combine those radicals and play a little math to make it a little bit easier. But you can see that this number, so 10/7 is less than 2, right? This is, I don't even know what that is. I'm not even going to play the game, but it's less than 2, right? This would go further. So if it weren't rolling, it would go further. But if it is rolling, we have to be able to account for that. Does that make sense? Does it follow or no?
Yeah, it does.
I'm following.
Okay. So as you deal with something that's rolling, it has rotational kinetic energy that has to be accounted for in some form. If it's flying, if you kick a soccer ball and it's spinning through the air, the rotational kinetic energy is there, but it doesn't affect its path as much as like the air drag, something we're not going to study this, the Bernoulli forces as the ball moves through the air when it's spinning either creates a lift or a down push, and we're not getting into that. So when we're doing rotational kinetic energy, we're going to be doing this, or we're going to be doing an object that's sitting on a platform and just spinning. Okay, so it makes a little difference if it's moving across the surface, and that we include translational kinetic energy as well. And translational just means is another word that just means in a straight line. Okay, the other thing we have not done or discussed is momentum. I think it's probably better suited for another discussion because it brings into discussions. In one of the labs, we did a collision with angular momentum, but I do want to do a better job at developing your understanding of that. So if you're looking in chapter 8, we've discussed sections 4 and 5 today, essentially. Yeah, I think that's about it. I'm looking at a book just to make sure I'm kind of in the right place. All right. Well, I think that's enough for the day. Anybody have any questions?